Good morning, everybody. I hope that you guys are having a good start to your day. I hope you enjoyed your weekend. Um, and I hope you got a good plan for the week ahead. I am recording. Um, I've got the PowerPoint open for chapter number 5, and I will be working through that today. If you look at the calendar, which I'm going to share that screen with you guys in just a second. Let's see what do we got. So if you look at the calendar here, this is my display of what we've got. Today is March 24th. We've got one, two, three, four, five, six, seven, and then 8 days of new content for this semester. On the 21st of April, we'll have a review for our third midterm exam. On the 23rd of April, we'll have that midterm exam. Then the 28th, which will be a Monday, we'll have our basically our prep for our final exam. And then on the 30th, we'll have our final. Um, so my long story short is that there's a not a huge a number of class periods left. And so, I don't want to get sad before the semester's over, but just to kind of give you a little bit of a heads up. Now, one thing that I wanted to do right from the jump was I wanted to talk about exam grades. I've got all the exam grades in, and so at this point, one of the things that you probably see is exam one. And under that exam one kind of umbrella, you see the score from E1 and the score from E2. Now, those two scores are a part of one category, which I believe that category is worth 15% of your overall grade. And so, let's say that you got a 90 on exam number one and an 82 on exam number two. Um, this grade right here, this 82, is not being used as a part of your grade calculation. Um, and that's just kind of how we're doing things. Um, that's where this exams are cumulative comes into play. So then exam two, we'll say that's going to be a category that's going to have E2 and E3. The 82 that you got on exam number two, that is being used as a part of this 15% of your exam two grade. E3, we haven't taken that yet, so there's nothing to include there. But I just want to bring this up because it's different. I hope that you guys, if you have any confusion or questions about it, please don't hesitate to contact me. I'll have office hours today, 12:30 to 1:30. So if you want to meet during then and just kind of play around with some numbers, I'm more than happy to do that. But if nobody has any questions about that, I'm going to go ahead and proceed. Does anyone have any questions? I'll give you a couple of seconds to think about that. Um, so if anyone has any questions kind of about anything, go for it. Otherwise, we are on to chapter number 5. Now, to put all of this into perspective, what we are going to do and what we've done so far is we will, or kind of what we'll cover over the course of the semester is all this, chapters 1 through 8. Now, oh, okay, so I got a couple of different messages. If I get a better grade on exam 3, it will replace exam 2. Yes. Another way to think about that is if you ace the final, then that is fantastic. Then basically you got on exams 1, 2, and 3 kind of don't really matter. That's just a little bit of a detail there. Do we not have any assignments this week? You do have assignments and quizzes, and I have not published those yet, but they will be published later this evening. I apologize for the delay on that. I'll send an announcement out whenever they are up. Um, yes. So thank you for your patience on that. Now we've covered what I wanted to go through with chapters one, two, three, and four, and we've got five, six, seven, and eight. When it comes to kind of the heavy lifting, the big parts of these chapters, I would say that chapter number five is really kind of the big one. Chapters seven and eight, we'll do those, but we're going to spend I think all told, about 2.5 days on those two chapters. Chapter number five and chapter number six, I have those out of sequence because historically I've done them out of sequence. Um, Now, this semester we're going to go five, then six. So we're going to follow actual numbers. But the one thing that I want to stress about chapter number six is there's a little bit more math. So I'm going to say that is math heavy. Now, in terms of how heavy are we talking? Well, I'll give you a little bit of an example. Um, we're going to be working this equation that looks like this: PV equals nRT. And that's known as the ideal gas equation. And basically, questions related to this right here will say, okay, well, if I give you a number, I'm just going to plug random numbers in here. For P, I'll say 5. V, I'll say 7. Then I'm going to say that is equal to N. I'm going to give you a value for R, 13, and then T is 22. So I've given you specific numbers, and in this example, they're all totally arbitrary. Um, what you'll need to do for this math heavy portion of chapter number six is solve for n. So is it trivial? No, it's not trivial, but it's you have four values. Can you solve for the fifth? Now, I know that there's probably somebody who's doing this calculation and they're about to add it to the chat and say, is it this? And I have not done the calculation, so I cannot answer that question. But can I get a Y as, okay, cool, I can follow that. And when we get there, I'm going to be good. Excellent. Excellent. Okay, so what we're jumping into chapter number five. This is chemical accounting. Is there anyone in this class, and add it to the chat if you are, is there anyone in this class who is a business or accounting major? Add a Y to the chat if you are a business or accounting major. Okay. Okay, good, good, good. Excellent. So what we're going to be doing a lot of here is it's kind of it's if you've ever heard the term business, if you've ever heard the term balancing equations, that's what we're going to be doing. We're going to be we kind of have a balance sheet, and we have to make this side equal to this side. Um, so that's what we're going to be working on predominantly and primarily with chapter number five. Now, as a little bit of a review, we've talked about physical changes. With physical changes, we've talked about what we're observing on a macro level. So when water boils, what does that look like? Then we've looked at things. So on the micro level, this would be where we look at our Lewis structures. So this is kind of representative of what's happening at the macro level. What we're going to get into here a little bit more is symbolic. We've talked about symbols, but we haven't gone too deep into them. We're going to be using symbols quite a bit more. Now we've looked at, using a formula like this and converting it to a structure. So basically what we're in chemistry, what we do a lot of is this kind of transition from, okay, what does something look at the macro level? What do we think it looks like then at the micro level? And then what's the symbolic representation of that? So here what we've got is water boiling. Then what we've got is black space between these molecules being produced. Okay, so there's space between them. And now summing that all up, what does that consist of? Well, that consists of H2O. Does anyone want to guess what this L stands for? Add it to the chat if you know what that L stands for, if you want to guess what that L stands for. And just as a little bit of an idea, this represents this right here, which represents also this right here. Liquid. Absolutely. Awesome. So we have a liquid transitioning to, now go ahead and add to the chat if you know what G. Perfect. Great job, Troy. Gas. So we've got a liquid transitioning to a gas. So all of these three things kind of describe and display the same thing. Now, we go on from there. We have our periodic table of elements, and this is where I want to introduce basically 7 elements that I need you to keep kind of put these in your memory and don't forget them. Another way of saying what I just said was memorize them. I don't know, there's a part of me that has this aversion to saying memorize. But memorize these. Okay. Now, whenever I was in high school, we had or my chemistry teacher taught me this, and everyone else. She taught us this mnemonic, and it was H. Broncliffe. Now this is an I right here. And she had this little character. It was like, here's the eyes. He's got glasses on. And then here's the nose. And then I'm gonna. Do you think H. Broncliffe has a nose? Yes, a nose, but a mustache. I'm gonna say yeah. I'm gonna go with yeah, kind of a Salvador Dali type of mustache. So this is a character known as H. Broncliffe. And H. Broncliffe is a mnemonic to represent all of the diatomic gases. So what this means is that these are elements that when they are in their what's known as our standard state or their elemental state, does anyone remember what the charge of something is when it's in its elemental state? When it's in its elemental or its basic state, its charge is zero. Neutral. Perfect, Giovanni. Fantastic. Thank you very much. Yes, great job, Haley. So it has a neutral charge. Okay. Now, if we were to take something like carbon, carbon in its elemental state is going to have a charge of zero, and it's going to be a single carbon atom. Okay. Now, H. Broncliffe, hydrogen, bromine, oxygen, nitrogen, chlorine, iodine, and fluorine. Those are all diatomic gases. What that means is they love to form a gas. Like at room temperature, what they are going to do is nitrogen, for example, you're never going to see a neutral nitrogen atom just floating around. Instead, what it's going to do is it's going to find another nitrogen atom and it's going to form N2 gas. Okay, so N2 is an example of a diatom, and N2 is an example of a diatomic gas. What that means is that these two identical atoms, they come together at room temperature and they are in a gaseous state. So at room temperature, they are a gas. Okay. So if I were to mention something like, oh, well, there's bromine at room temperature, what's kind of implied there is that it's Br2. Okay. So those are your diatomic gases, and I want you to commit those to memory. And I always just remember, and I hope that my wonderful art skills will help you remember H. Broncliffe, and then you can just kind of parse it out and say, okay, H is hydrogen, Br, bromine, O is oxygen, N is nitrogen, and so on. So H. Broncliffe are the diatomic gases. And so what that means is that if you go outside and you inhale, what you're going to get is you're going to get a lot of oxygen, but add to the chat what form that oxygen is in. Spoiler, you're inhaling a gas, yes, but is it O? Is it O3? Is it O4? Is it O minus 1? O2, perfect, perfect, wonderful. Okay. Also in the atmosphere, when you go outside and you inhale, you're going to get some nitrogen. What is that nitrogen going to exist as that you've inhaled? N2, perfect. Okay. So can I get a Y, okay, cool, I got it with respect to diatomic gases. And yes, I can memorize those and I'm good to go. Okay, awesome. Fantastic. Um, if anyone wants to do a screenshot of my picture of H. Broncliffe, um, what were those things a few years ago that were NFTs? We can make sure that's an original and it'll be worth millions of dollars on the crypto blockchain exchange. Haha. Okay, so we'll proceed from there. Now, what we're talking about today and what we're going to be getting into are chemical reactions. We've already kind of looked at some of these, but now we're going to be talking about what are the kind of parties involved. This is a great example because it highlights O2, one of our diatomic gases. Now, this is what this video shows is a block or a chunk of carbon. Now, what this black substance right here, is it is a solid at the macro level that is at the micro level just a bunch of carbon atoms. So I would say quadrillions of C atoms. Those are all kind of packed and clustered together. Now, what this video shows is that if you spray O2, like if you get an oxygen tank or something and spray it on there, what's going to happen is it's going to kind of ignite. And whenever it ignites, it's going to produce CO2. Now, let me ask you this. Whenever we talk about diatomic, but let's write the whole word out, Joel. I don't need to have such a stern tone with myself. Okay, whenever I say diatomic, what does the DI stand for? Perfect. Two. Now I'm going to ask you this follow-up question. Is CO2 a diatom? Or is CO2 a diatomic gas? Add a Y for yes or an N for no. I know it's tempting. Okay, we got split decision on this one. This is not. And the reason it's not is because, well, think about CO2 as a molecule. So I'm not drawing all the extra electrons there, but how many atoms is that? Three. So that is three atoms. Great job, Dolce. So that's three atoms. So it's not a diatomic gas. It's not a diatom. And I say that it's tempting just because you kind of get in this habit of like, oh, okay, H2, Br2, O2, N2. Ah, I got it. I got my diatoms. And then you see O2 and you're like, I think that must be it. Yes. But this right here, this O2 is not the same. CO2, yes, CO2 has three atoms. Absolutely. So CO2 and O2, not the same. Okay. Now, with that in mind, CO2 and O2 are both gases, but one of them, I always like to think about it as one of them you want to inhale, and one of them you want to exhale. Now, what this shows is our reactants and our products. Anytime you look at a chemical reaction, there's a couple of things that I want you to recognize. This arrow right here. I want you to also recognize the things that are on the left-hand side and the things that are on the right-hand side. Now, if you look at this, one thing that I want you to recognize on the left-hand side is that we've got, well, one, two reactants. And then how many products do we have? One. You're absolutely right. It's only one product over there. And this one product, this is kind of bringing back like chapter one, chapter two language, but this is one molecule. So what we have here is an atom of carbon reacting with a molecule of O2, ATOM, to produce one molecule of CO2. So this is just an example. Now I'm going to go on to the next slide because, well, we can have, let's go with C6H6. That is a molecule. That is an example of a molecule reacts with O2. And this will produce CO2 plus H2O. Here what we have is molecule plus molecule to produce, well, two products, molecules and a molecule. So if we can kind of compare those two, I want you to look at this and not necessarily think, okay, what do I have to have for a chemical reaction? Does it have to be an atom and a molecule reacting to form a molecule? No. What I want you to recognize here is I want you to think about, well, what's on the left-hand side and what's on the right-hand side? In this specific case, I've got an atom that reacts with a molecule. Okay. And then on my product side, I have one single molecule. Okay. Now, if we can jump ahead, I want you to only look at what's on the right-hand side here. What's on the right-hand side? Well, those are where my products are formed. On the right-hand side of this reaction that's shown, how many different molecules do I have? On the right-hand side of my reaction, I've got two molecules, and that's exactly right. So we've got a variation here. Here we have one molecule that's produced. Here we have two molecules that are produced. Add to the chat a Y if you think that it's possible that we could have three molecules as products. How about three molecules and one atom? Do you think that's possible? Yep. In the words of Kevin Garnett after the Celtics won the NBA title in 2008 or 2009, anything is possible. You're absolutely right. There's a number of different variations there. I want you to be able to use this terminology and use this language and kind of go back to the deeper in the recesses of your memory of, okay, what's an atom? What's a molecule? So one of the things, though, that I want you to recognize, and this is the biggest part about balancing a chemical reaction, is I want you to look at the reactants and products. And now answer with a Y for yes or an N for no Are the numbers of carbons on the left and right hand side, on the products and reactants side of this equation, are the number of carbons equal? We got some solid N's there. Emily hit us with a capital N right off the bat. Juan as well. That sounds like a defiant. That's like an N with you stuck your trident in the ground to say no. You're absolutely right. The numbers of carbons are not identical. What about oxygens? A Y for yes and for no. No, they're not. How many oxygens do we have on the left-hand side, on the reactant side? Add that to the chat. How many oxygens do we have on the right-hand side, on the product side of my reaction? We got three. Perfect. Okay, so there's an imbalance there. So this is like understanding that is the core of balancing a chemical reaction. If you can understand that, that's the first step towards, solving the problem. It's kind of like recognizing the problem is the first part of solving the problem. So, what this all relates to, though, is conservation of mass. It also relates to, well, another model of conservation of mass, where we see things where we see a chemical reaction. We had mercuric oxide break down into mercury and oxygen. We have vinegar added to baking soda to make CO2 and water. Now, this right here is essentially what we're going to be doing. And if you can answer those simple questions like, is this balanced? Yes or no? That's like your entry level easy question. Then the next thing is, well, statements about balancing a chemical reaction. We got this one right here and this one down here. I'm going to circle a number and you add to the chat if that's a coefficient or a subscript. I'm going to circle a number, and if it's a subscript, type subscript, or just type S. Or if it's a coefficient, type C. Add it to the chat starting now. Nice. Seeing lots of S's there. Now I'm going to switch my number. I circled another one. Is that a subscript? Nice. Okay, well, I'm not going to repeat that over and over again, and instead I'm going to throw this one to you. Coefficient. Perfect. Now, if you guys are considering what sort of forearm tattoo should you get this weekend, um, there's a number of different recommendations. Find your favorite death metal band and get their like logo. Like if you're a Slayer fan, get that. Alternatively, you could get a good rule of thumb for chemistry, and that is change coefficients. I don't know. I don't know. It's well, no, actually, Delta, I do know. The I knew that because, it's almost the end of the month, and everyone always was like, I need to get a good forearm tattoo at the end of the month. So that was my guess. So your forearm tattoo suggestion, recommendation, just thought, um, change coefficients, not subscripts. That also sounds like I don't know, like an anti-war protest. You could get that on you could put that on a poster board and march outside City Hall. Change coefficients, not subscripts. Um, those are the rules. Or that's, sorry, not the rules, but that's like one of the most fundamentally important rules of balancing a chemical reaction. You can change coefficients, but not subscripts. If you follow that, you're going to be in fantastic shape. Because if you look at, well, our balanced chemical reactions and our unbalanced chemical reaction, up top here, H2O. Let me throw this option at you. Answer with a Y, yes, it's the same, or an N, no, it's not the same. H2O is the same as H2O2. A Y for yes, it's the same, and Emily, right, absolutely right. No, it's not the same. So H3O, not the same. it's so tempting when you see a balanced chemical equation, or so let me rephrase that, an unbalanced chemical equation. It's very tempting to look at this and say, "Oh, well, I know how to balance this. How about done? Yeah, I'm done. I fixed it." Well, when you did that, you changed water to hydrogen peroxide, and you said hydrogen peroxide breaks down to H2 and O2, which, okay, let me bring this back to you. Add a Y for yes, they are, or an N for no, they're not. Um, H2 and O2, are these diatomic gases? These are the same. Yes, they are. These are both diatomic gases. Okay, so it's super tempting to just change the subscript and move forward with your life. But we can't do that. We only can change coefficients. Now, when you look at something like H2O, water, breaking down into H2, how about right? H2, not H2O. Sorry, muscle memory there. H2 and O2. Now, we've done Lewis structures, so I think that it's helpful to kind of use that as like a tool. We've got oxygen, hydrogen, hydrogen. What is H2 going to look like? It's going to look a little bit like this. What is O2 going to look like? Again, like this. Are there some double bonds on that O2? Probably. Are we going to stress about that right now? Probably not. And when I say probably not, no, we're not going to. Um, what I always like to do whenever I do something like this and whenever I draw these symbols is I'll say, okay, well, how many oxygens can I do I actually have to work with? Well, I've only got one in my reactants. So with just H2O, is it possible, add a Y for yes or an N for no, is it possible for me to make this from one H2O molecule? From one H2O, I know, you're right. I did. And no, I can't. Yeah, this is kind of like a forlorn face. Yeah. Okay. I'm not going to draw another H Braun cliff. Um, okay, so you're absolutely right. I can't. How about if I do this? Add a Y for yes, I can make O2, or N for no, that I can't. And I'm just thinking about, do I have the resources? Yes, I do. Sorry, John, whenever I've got these two H2, I gotcha. Thank you. Um, whenever I'm, whenever I have my two H2O molecules, I've got what I need to make this right here. Okay. Now, follow-up question. Do I have what I need to make an H2 molecule? So I'm going to put a check by that. Yeah, I've got enough to make my H2s. So I'm good there. And so what I always like to do whenever I'm just kind of working through this is I'll go ahead and scribble through that and that because I've used those to make my O2s. What about my H2? Yeah, I'll go there and then yeah, there. So I've made an O2 and I've made an H2. What's left over? Well, two hydrogens. So I actually have enough resources that I can make that right there. So this is an instance where people like to um they kind of treat this almost like um a recipe. Balancing a chemical reaction is a really good example of kind of a recipe. Like if you ever bake bread or something like that, which if you haven't baked a loaf of bread, I would strongly recommend doing it. It's really therapeutic. It's really fun. And go ahead and add to the chat Y or N if you agree with the statement that homemade bread is better than store-bought bread. Yeah, totally. And if you're an avocado toast person, um, that's gonna severely help your avocado toast budget. So, the homemade bread will help out a lot. And then if you have 10 to 15 years to grow an avocado tree in your yard or in your home, well, that will also help with your avocado budget, or avocado toast budget. But my point is, if you make bread and you're like, okay, well, I've got all this dough, but I've got some extra. I made a loaf that was this large and I've got some extra. What can I do with it? Well, what you could do with it is you could make like I don't know, like pigs in a blanket or something like that. And you just have that extra. Or you could, rather than making it a loaf, weave it into like a challah bread or something like that. So making something extra. So that's what we've got. We had to bring in that second H2O molecule to get us to our O. I'm not sure what FS stands for. For sure. Oh, for sure. Probably, I'm guessing. Or I hope it's not swear words. Um, we brought in our second H2O molecule, which got us enough of our resources to make O2, but we kind of, oh, well, we still had enough resources to make H2. Okay, thank you very much. That's what I was thinking after I said it aloud, but okay. So, balancing chemical reactions. I will say that is kind of as that's what there is to it. Um, Play around with coefficients. Don't alter subscripts. Um, and you're going to be in good shape there. Now, here what we have is another symbolic representation. This is an example where I believe these are black beans and kidney beans that were used. The kidney beans represent the O2. Actually, here, kidney beans represent the O2, and the carbon is represented by black beans there and there, respectively. We had to bring two of them in, which would get us two molecules of carbon monoxide. So, whenever it comes to like answering questions about balancing chemical reactions, um, lots of the questions that I will give you on exams and quizzes are going to be, well, is this the correct coefficient? And that's kind of what I'm going to be looking for most often. Now, there's this tool right here that gives us a, a way to play around with balancing chemical reactions. And I thought I had that up in my browser, but it seems to be on the fritz. So what I want us to do is, well, we're just going to play around with this. We've got, let me ask you, and go ahead and um, add to the chat with numbers. Let's say that I've got, and I'm going to draw this N2. If I have N2, add to the chat your number for how many NH3s can I make. If I have N2 only, how many NH3s can I make? Got me. Right. If I only have N2, so sorry, this box is where I'm going to be drawing kind of, think about it as my resources. And then here I've got my products. So if I only have N2, I'm not going to make any NH3. Let's say that I add in H2. Oh, well, this changes things. Now I've got both of the atoms that I need. Can I make any NH3? Down below, I'm going to draw a model of what I need. NH3. Um, I'm seeing zeros there because you're right. I'm not going to be able to make any NH3s. Let's say that I add another NH2 or N2. Now add how many NH3s can I make? Nobody's adding anything because you're absolutely right. Zero. It's still zero. If I add a million N2s, Am I going to be able to make any NH3s if I only have one H2? I'm not. What that tells me is it's almost like it doesn't matter. And I don't want to get, or I don't mean to like impart philosophy on you or anything like that. But let's say that you got $1 trillion. If somebody got $1 trillion on their deathbed, oh yeah, they have $1 trillion. Great. But they're they don't have any time left. So it's almost like it doesn't even matter. Yeah, I went pretty deep on that, pretty hard and pretty deep on that. Okay, I apologize. I'll bring it back. Here we've got N2. We've got two molecules of N2. Awesome, great. But we don't have enough H2 to actually do anything because we need three hydrogens. And with H2, we only have, well, two hydrogens. We add in one more. Okay, now add the number of NH3s that I can make with this combination on my left-hand side. How many NH3s can I make from what's shown on my left-hand side? Make one. And again, what I like to do is I like to cross things out and say, okay, well, that's in use. So I'm going to scribble out a nitrogen. One, two, and three. Okay. So you could look at the nitrogens that are shown on the left-hand side and everything that's shown on the left-hand side at this point in time and say these are excess because I haven't used them. Now, what I want to do is I want to build up the nitrogens and hydrogens and basically get complete use of all of them. Now, my question for you guys is what should I add more of, N2 or H2? Add an N for nitrogen or N2 and H for hydrogen, H2. So I can add another one. Okay. And whenever I do that, now I've got enough for another NH3. So I'll scribble these out. Okay, so this looks to me like a really good ratio. Would you agree with me that N2 is in complete excess? Yeah. Now you could look at this and say, oh, well, if I added more H2, then I could make more NH3. Would everyone agree with that statement? If I add more H2, I could make more NH3. Add a Y to the chat for yes or an N for no, I don't agree. Okay. Now, my follow-up to that question is add a Y for yes, I need to, or an N for no, I don't need to. I could just get rid of that excess N2. I like it. I'm going to get rid of this because this shows me a balanced chemical reaction here is one, two, three H2s gives me two NH3. Now, does everyone follow that right there? Add a Y for yes, I'm good, or an N for no, I don't follow. Okay. Now, I'm going to bring back this idea of like a recipe. Okay. What Anytime that you balance a chemical reaction, you want to get the lowest possible ratio. So it's kind of like when you're cooking something. If you're going to make cookies, you might say, okay, well, let's go with 2 cups flour, 1 cup sugar, 1 cup chalk chips, let's say 1 cup milk, 1 teaspoon salt, and this is my last ingredient. I'm gonna up it to 2 cups of milk. And then let's say 1 teaspoon vanilla extract. Okay. Now, think about this as a recipe for cookies, but think about a recipe for cookies as being like a balanced chemical reaction. Okay, would you describe these as your reactants or your products? Add an R for reactants or P for products? Reactants. Because our products, what are our products whenever we're baking cookies? The cookies. So these are our reactants. Sorry about I was building up to something, but my cookies are my products. And let's say from this specific recipe, um, let's say that we can make from this recipe 24 cookies. Does everyone follow me right here with respect to my reactants and my products? Okay. Now, what would happen to the numbers of cookies that we could make if I took everything, all of my reactants, and doubled them? Instead of 2 cups of flour, I use 4 cups of flour. Instead of 1 cup of sugar, I had 2 cups of sugar, 2 cups of chocolate chips, and so on. How would my number of cookies change? Yeah, I'd be able to make 48 cookies. I'd double my recipe. Now, I'm maintaining the same ratio of reactants to products. When we're doing a balanced chemical reaction, we're doing the same sort of thing. We want to find out what's the minimum ratio that we have, minimum whole number ratio. Um, and whenever I say whole number, let me ask you this. Is zero point 0.5 a whole number? 0.5. No, it's not. Not a whole number? Great. Okay. So is 1 a whole number? Add Y to the chat or an N for a no. Y is a whole number. Okay, so now let's bring this back to my balanced chemical reaction. My 1 to 3 to 2. 1 N2 plus 3 H2 yields 2 NH3. My question for you guys is if I went to 2 N2 plus 6 H2 yields 4 NH3. Would you agree with that statement that I could use 2N2, 6H2 to make 4NH3? Add a Y to the chat if you agree that 2N2 plus 6H2. Great. Now, can these numbers, 2, 6, and 4, can they be reduced at all? Yeah, I could reduce that to, well, 1, 3, and 2. Does everyone agree with that? Now, my follow-up to that is, can I reduce 1 and still have a whole number? Add a Y for yes and N for no. No, I can't. If I reduced 1 to anything, it'd be zero point 0.5. So this right here, that is my minimum whole number ratio of reactants to products. That is what I'm aiming for whenever I look to get a balanced chemical reaction. Does everyone follow that? Okay. Now, if I doubled it, would I still make the products? Yeah, I would. If I tripled it, I'd make even more. Just like our recipe for our cookies. If I increased the amount of flour, sugar, if I increased all of the reactants, all of the ingredients, would I make more cookies? Yes, I would. if I cut, if I took these numbers right here and I cut them in half a cup, half a cup, 1 cup, half a teaspoon, would I still be able to make cookies? I would. How many cookies? Well, fewer. You can reduce those numbers and still make the product, but you're not going to make as much as the minimum whole number ratio. Okay. Can I get a Y in the chat if you're good to proceed, or an N if you want another example? Okay. Okay. Awesome, guys. This is great. This is great. So this right here are just some examples of chemical reactions and how they can be balanced. So if we've got, let's go ahead and do these and then we're going to call it a day. Deal, add a Y for a deal, an N for no deal. And I kind of don't really give you much of an option. This is where I wanted to get. So we've got NaN3. That is, add P for product or R for reactant. What is NaN3? Is that a product or a reactant? Add that to the chat. It's a reactant. Okay. So here what we can do is we can play around with the coefficients. And what you'll notice is that we've got, well, one molecule as a reactant going to one atom and one molecule as products. NaN3. The first question to ask whenever you look at something like this is say, well, how many sodiums do I have? I've got one sodium on each side of the reaction. So is there anything to do right now when it comes to balancing balancing the sodiums? Nope, they're good to go. Let's see what else. Or sorry, I made a typo. A righto, as it would be. NaN3 decomposes to Na plus N2. Um, N2, are those balanced? They're not. So how do we do that? Well, one thing that you could do is you could just plug in a number and say, okay, well, N2, that's lower than N3. So what I'm going to do is I'm going to put a 2 out in front there. If I put a 2 coefficient in front of N2, how many nitrogens will I have on my product side? Add that to the chat. 4. Now, I've got 3 on the reactant side. Is 4 the same as 3? Nope. So, does the 2 really get us anywhere? It doesn't. So what I want to do is I want to go up from 2. So I'm going to say 3. Okay. So now I've got 6 nitrogens on my product side. How many do I have on my reactant side? I've still got 3. Does anyone, oh, Haley, you jumped in front of the question I was going to ask. Haley's question, or the question I was going to ask that Haley answered was, what coefficient should I put in front of the NaN3? I should put a 2. Now, does that balance my nitrogens? It does. But what does it present a problem? Maybe not a minor problem here. It does present a little bit of a problem because now our sodiums aren't balanced. So how do we resolve that? 2. So this is one where we we added a coefficient here, so then we had to add a coefficient here, which caused us to add a coefficient here. We kind of volley back and forth. What are the consequences of adding this number? Okay, well, what happens when we do this? What happens when we do this? Can I get a Y in the chat if you followed that? We kind of jump back and forth. Okay. Okay, cool. So now I'm going to go down to the next example. Fe2O3 plus C yields Fe plus CO2. So again, we got coefficients. That Fe2O3, I'll be honest, part of me looks at that and says, well, I'm probably not going to throw a coefficient in front of there because there's already a bunch of subscripts. But I'm going to be open to the idea that I need to. So I'm going to put a coefficient in front. Now, let's see, Fe2O3. I've got 2 iron, 3 oxygen, 1 carbon. Then I've got 1 iron, I've got 1 carbon, and 2 oxygens. I always like to kind of survey the landscape. And then, just as a recommendation, it's a it can be a good idea to start with carbons, or sorry, start with oxygens. I've got 2 on my product side, 3 on my reactant side. Well, just as we saw up here, we didn't go with a 2. Instead, we went with a 3 because these will end up equaling 6. So I'm going to put a 3 coefficient in front of CO2 because that will mean now I have 6 oxygens on my product side. Then I'm going to put a 2 coefficient in front of Fe2O3. That will mean that I've got 6 oxygens on the reactant side. So now my question is, with those 2 coefficients, are my oxygens balanced? They are. They're good to go. Now, what are the kind of consequences of that? Well, I've got 6 oxygens. Now add to the chat the number of irons I have. 4. Well, on my product side, I have Fe. There's no subscript there, so I'm just going to throw a 4 out in front. Balanced. So now, what atoms have I balanced? I balanced my oxygens. I balanced my irons. What atom is left to balance? Carbons. And Haley, you're right. Now, did that look complicated from the start? I think so. Was it complicated when we started with focusing in on one atom? I don't think so. What did we have to do? We had to add a coefficient and say, okay, what are the consequences of adding that coefficient to react or on my product side? Now, my question for you guys is, did we start on the product side or let me rephrase that. Do you think that we would have come up with the same answer if we started on the reactant side? Add a Y for yes or an N for no. If we had started on the reactant side, would we come up with the same answer that we came up with? We got a vote for no. Got some votes for yes. Now, we started on the product side. I'm going to start on the reactant side. I'm going to erase these. And we've got them there. We know it. But let's go ahead and try it. We've got 3 oxygens on the reactant side. We will do I got a private message. Are we not doing poll questions on Zoom anymore? We will, but I just don't have any today. So we will have them. So we've got 3 oxygens on my left-hand side. I'm going to put a 2 coefficient out there. So now what do I need to do on my right-hand side? There are 3 coefficient in front of that CO2. Okay. So my oxygens are balanced. What about my irons? 2 and 2. That brings us 4. Done. What atom is left to balance? Carbons. It's the exact same answer had we started on the reactants or the product side. So I want you to go in with a mindset of, okay, where should I start? Does it matter if I start on the reactants or the product side? It doesn't. Which atom should I start with? Well, it's probably a good idea to start with something like oxygen. Okay, everyone, that's what I've got for you today. I hope that you had a great day. Thank you very much for your participation answers. You guys did a great job. I'm going to stop my recording. I've got office hours starting at 12:30 if you want to drop by. Same link as always.